Hi everyone, this is David Singletary. This is COP2073C, Introduction to Statistical Programming with R, and this is Module 3, Extended Data Types and Data Structures. In Module 3, we're going to work our way up the ladder of complexity in our data types and get into lists and data frames, a very common data type used in R, but we need to cover some fundamentals first. We've already seen the logical value operations where we have true and false, or abbreviated as T and F, where these values are binary literal values, and we can use them in vectors and matrices. This is assigning the value true to a single variable x, assigning false to a variable y, and we can create a vector of logical values. So 4 logical values, true, true, false, false, and then displaying the value of that vector. We'll see that we can use these throughout our data types, regardless of how complex they get, and they'll be useful in doing some of our relational operations. We have the relational expressions, which do comparisons of single values, and these are very common to most other programming languages where we also have these operators to compare for equality. We have the double equals, no space in between. This is different from assignment. Now remember, we have the arrow assignment operator in R, so it's not really relevant to discuss the single equal sign except in the use of named arguments, but the double equal is used for comparison for equality. The exclamation point equal, or bang equal for short, for not equal, and then the typical arithmetic comparison operators greater than, less than, greater than or equal to, and less than or equal to. To use these operators, we'll just try them with some literal values first. You can see if we use 1 compared to 2, we get false, obviously, because those aren't equal. 1 is also not greater than 2, so that's false. 1 is less than 2, so we get true. And 1 is not equal to 2, so we get true for that also. You notice when they display these logical values, you'll get the full word. You don't get the abbreviation. And then we can use some variables. So assign 10 to x and 20 to y. X is not equal to y, so this is false. X is less than y. X is not greater than y. And then x not equal, and we get true for that expression. So very similar to how these operate in other programming languages. When we get into the higher level data types, though, we'll see R's implementation of these operators is more powerful because we're doing vector-oriented behavior here. So we have this vector 1, 2, 3, 4 being assigned to v1, and 2, 2, 3, 4 being assigned to v2. These are not equal because you have one value that's different, the 1 and the 2. But notice that the comparison produces a vector of logical values, not a single value. And so it does element by element comparison, comparing the first element, which is not equal, and then the second, third, and fourth, which are equal. So we get a vector of those logical results. The not equal, this just inverts the result of the last operation because 1 is not equal to 2. But then for the not equal, you see the other 3 elements report as false for those comparisons. v1 less than v2, element by element. 1 is less than 2, that's true. The others are equal, so they're not less than, so they report as false. And then v1 greater than v2, 1 is not greater than 2. And again, the equal state of those other 3 elements results in false for all the elements of this vector. We talked about recycling in the last module, and it works with relational comparisons as well. We've got a vector v1 from our last slide, same values here, 1, 2, 3, 4. We're creating a new vector z and assigning this vector with 2 elements to it, 2 and 3. And so now we've got this 4-element vector, and we want to compare it to the 2-element vector. Because of recycling, we're going to compare the first 2 elements, and we're doing v1 less than z. So we do element by element. 1 is less than 2, and 2 is less than 3, so that's true for both of those. Now we've run out of values in this 2-element vector z, so we recycle it. We get 2 and 3 again, and we continue with the element by element comparison. So now we're looking at, is 3 less than 2? So if we just match these up, that's false. And is 4 less than 3? And that's also false. So recycling works with relational operators. When we do relational operators with matrices, it's a little bit different in behavior because it does a column by column comparison, not row by row. So we have this matrix M1, and we've combined the two vectors V1 and V2 into this matrix. So it's a 4-row by 2-column matrix. We're defining this 4-element vector of values 2, 3, 4, and 5 and assigning it to Z1. And now we compare M1 less than Z1. So we've got 8 elements we have to check against this 4-element vector. And so it does an element by element but column-wise comparison. So M1, the first check, is V1, the first row and column. And is 1 less than Z1, the first element of Z1? It is, so that's true. And then we check the next element in the same column. So is 2 less than 3? Yes, it is. 3 is less than 4, and 4 is less than 5. And then, after we worked our way through this column, we move to the next column and do element by element again. Is 2 less than 2? No, it's equal, so we get false. And then the subsequent checks, 2 is less than 3, and 3 is less than 4, and 4 is less than 5, and we get true for those. So you see we have this column-wise operation for relational operators when we're working with matrices. Now, logical operators are similar to relational operators in that they do comparisons, but we do combinations of relational comparisons using logical operators. So they're kind of like a glue for relational expressions, where they'll glue multiple expressions together. The result of any logical operator is the same as a relational expression. It's true or false. R provides some slightly different versions of the logical and logical or operators. The logical and is the ampersand, and this is very common among most programming languages. And the idea is that every expression that's combined with this logical and has to be true in order for the overall expression to be true. So if we had two true relational expressions, the logical and between them, the fact that they're both true means that this will be true, the overall result. If we have a true expression and a false expression, then the whole expression is false because they both have to be true. If one's false and true, well, that's just a different ordering. They're still false. And then false and false is definitely false. So I refer to the logical and as the pessimistic logical operator because there's only one chance of getting a true result from it. That's only if everything in the expression is true. And this holds for more than two relational expressions. You can have as many relational expressions in here as you want, and they will all have to be true for that logical value to be true. Now, this is the single ampersand operator. It's an element-wise. So if you use this in vectors, it'll do element by element comparison. The R also provides a double logical and operator. This is for a single comparison, and the behavior is fairly unique for this, and we'll look at an example on the next slide. Continuing on here, we have the logical OR. That's the vertical pipe. This is the key above the backward slash on most keyboards. Logical OR is what I call the optimistic logical operator because when you combine relational expressions, only one of them has to be true for the entire expression to be true. So two relational expressions that are true, true and false, or I should say true or false. One of them is true, so the whole expression is true. False or true, just a different ordering, also true. So the only result where the whole expression is false is when everything in the relational expressions evaluates to false. So again, this applies to two or more relational expressions. And so if any one of them were true, no matter how many you have, the result's going to be true. Only if they're all false will you get false out of this. And finally, we have the not operator, the exclamation point or bang. This just inverts the expression. So putting the exclamation point in front of true results in false, and putting exclamation point in front of false results in true. This looks fairly simple, but this can be very useful in complicated expressions where you want to just negate the whole expression. And again, this is similar to other programming languages in its behavior, and there is no special version of that. We only have the single exclamation point. So let's take a look at the differences between the two versions of the logical AND operator, and then we'll look at the same differences between the logical OR. The informal name for this is the long AND and the short AND. The long AND is element-wise, which means it looks at all the elements in the expression in the vectors. The short AND is a single comparison, and it only looks at the first elements. Easiest way to look at an example here is just to use logical values and do the comparisons with those. We've created a vector here of logical values true, false for x1, then all true for x2. And so using the element-wise comparison, you see when I do the comparison here, it's comparing in a column-wise fashion if we line these up as if they were in a matrix. The first two trues results in a true, the false and true results in false, and then we have two trues again is true, and then false and true again, which is false. So that's the element-wise AND operator, where you see they're comparing each element of the two vectors. Now compare that to the short version of the AND operator with the double ampersand here, and we're not looking at anything after the first elements. So these three elements are not being examined. We're just looking at these first two and doing the comparison, and that gives us a true. Now if we bring in another vector, let's set this x3 to all false. When we do our comparison with the short logical AND, we have to go left to right. So first we're doing the x1, x2 comparison, which we did up here, and we got true, and then we continue with the first element of the x3, which is false, and so the single true and the single false with a logical AND results in a final result of false. Then we have the long and short OR operation. Single pipe is the element-wise, or the long logical OR, and the double pipe is the single comparison. Compares only the first element. Doing the same exercise like we did on the last slide, we've got our true, false vector for x1, all true for x2, and so if we do the column-wise, the logical OR, we're going to get 4 logical results from those comparisons, and they're all true because, again, this is the OR where only one of those needs to be true for the whole expression to be true. Using the short logical OR operator, the double pipe, we're looking at the first elements, which is true and true, and so that's true. Now we bring in x3, which is all false, but our last result was true for the first element, and we're only looking at the first element of x3, here false, but we have a true or false, and so we get a final result of true from that expression. The NOT operator inverts the expression. Whatever you have here, in this case we're doing the short AND operation with x1, x2, and x3. Our final result is false, so it's very simple to put the exclamation point, the bang, in front of a parenthesized version of that expression, which evaluates to false, and it just switches it to true. And same here where we have the short logical OR operation, which results in true, put our logical NOT operator in front of that, and it just inverts it to false. Between the logical AND and logical OR operation, there is an order of precedence, and so you have to take that in consideration. So a simple example here, we've got a vector v1 that has values 2 and 3, a vector v2 that has values 1 and 2, and a vector v3 has values 3 and 4. So let's look at a simple long logical AND operation first. This is the element-wise operation. So v1 less than v2. That's asking the question, is 2 less than 1? v1 and v2. That's false. And then asking the question, is 3 less than 2, which is also false. So we're going to have a false result from this operation, and then we're doing the element-wise, or the long logical AND with v2 less than v3. So v2 has 1, and then 3. 1 is less than 3, and then 2 and 4. 2 is less than 4. So this expression is true, but when we take the combination of results from v1 less than v2, the two falses, and do the logical AND in an element-wise fashion with the two trues from here, because it is a logical AND, you get the two falses resulting here. And then we flip it, and now we're doing v2 less than v3. So 1 is less than 3, 2 is less than 4. So this is true. And then v1 less than v3. So is 2 less than 3? Yes, it is. Is 3 less than 4? Yes, it is. So this is true. And it doesn't really matter that they're both true because it's a logical OR. And so if only one of those pairs of expressions was true, then we would have enough to give us an overall true value. But since both are true, that's also the situation where we have true resulting from both. Now that's not showing the order of precedence. So let's look at that in an example here. The AND has a higher precedence. So by default, the AND operation is evaluated first. So if you remember from up in this first expression, this logical element-wise AND resulted in false, false. So we have false values here, and that was evaluated first. Now we come in and we bring in this logical OR, v1 less than v3, which we found was true in the previous example, and the fact that we have the true values here makes the entire expression true due to that logical OR. Now let's flip it and try putting parentheses around the OR to make it evaluate first. So we have v2 less than v3, v1 less than v3. Up here that was true, so we have a true expression. But then we're bringing in, after that's evaluated with those trues, we're bringing in the logical AND of v1 less than v2, which we found was false in the previous examples. And so we have a false and a true, which with a logical AND results in an overall false. Logical values can be treated as numbers in R. This is similar to other programming languages. We use the literal value 1 a lot of times instead of the word true. But in R, it's an actual keyword, but you can also treat it just like the number 1 for true, and false 0. So we have two trues, and we can actually add those together, make them look like an arithmetic operation, and the result is 2. And you notice it does the conversion automatically for you. Adding false, true is 0, 1, 0, 1, which is also 2. And then false, with its internal representation is 0. Add those together, you get 0. Logical subsetting in R is a very powerful feature where we can use the logical values to determine which elements to select from a parallel vector. We've got a vector V with the values 10, 20, 30, and 40. And then our logical vector, F, false, true, false, true. And so we can use this as a mask, this logical value vector as a mask to determine which elements to select. It's going to select anything that's true. And so we put the vector F as an index inside the square bracket, and it matches up the logical values with the numeric values and returns any of the numeric values that have the matching true value. So you see here that 20 is associated with a true in that logical vector, and then 40 is associated with true. And so by putting this logical vector inside the numeric vector as an element access operation, it extracts those two values. Here we have the numeric vector 10, 20, 30, 40. And now instead of using a logical vector, we're using a relational expression, v greater than 20. This is going to do an element-wise comparison of all the elements in V and pick the ones that are greater than 20 and return true for those. So you're going to have a logical vector result here of 4 elements, and it will be false for the elements that are less than or equal to 20. So first element and second element, both of those are going to return false for this relational comparison, whereas 30 and 40 are both going to return true. And so putting the v greater than 20 expression inside the extraction notation for the vector v results in those last two numeric values being extracted from the vector. And it's not limited to numeric values. We can do a text vector as well. We have 5 names here, and we're doing an alphabetic comparison of names greater than Monica. Now remember, this is the lexicographic ordering here, and so anything that is in terms of the sorting order of these letters greater than M, and then the remaining letters of the word Monica, is going to return true. So David doesn't make the cut, Fred. Monica is equal, so it's not greater than, so that also doesn't make the cut. And then Talia and Yolanda are the only results of that expression. And we can use that feature to assign values as well, not to just extract them. So here we have that vector of numbers 10, 20, 30, and 40, and our expression is the numbers are greater than 20. So those last two, the 30 and 40, are going to be true. And for those elements that match up with the logical result mask, we're going to use the extraction notation to do an assignment. So we're getting the last two of the four elements from that vector and assigning those last two elements the value 100. So you see the final result here, 10, 20, 100, and 100. And then the same type of operation here for the text array. Names again, David, Fred, Monica, Talia, Yolanda. We're going to look for the name Fred using the double equal comparison for equality. And when we find it in the vector, which is here, we're going to replace it with the name Frederick, the long form. And you see the resulting vector here is replaced Frederick with a long form of that name and left the other elements alone, since there's only one matching result from that expression. There's a function called which that identifies the element indexes that are true for this type of expression. We have a vector f with the values false, true, false, true. The which function with f passed as an argument identifies the true elements. So you see we get element 2 and element 4, the index values of that vector that are true. We have a vector 10, 20, 100, 100. V less than 100, it matches the first and second elements of that vector. So the which is useful for getting the numeric index values, not the actual values, but the index values of those matching elements. And so using this, we can remove values from our vector. So here's our modified vector again, 10, 20, 100, 100. And we want to find anything that is greater than, actually greater than or equal to 100 and remove it from the vector. So here is the which function. The expression is v greater than or equal to 100, does an element-wise comparison with each vector element, and putting the negative sign in front of the which function, and then putting the whole thing inside the square brackets for the extraction. Then we remove anything that is greater than or equal to 100, and you see the resulting vector here has just those first two elements that are less than 100. And then our logical subsetting works with matrices. So here we have a matrix M1 that has two vectors, column-wise, V1 and V2. So we're using the expression M1 greater than 2, and we're going to do an element-by-element comparison here. And so we get the first column is 3, 4. Remember, we work in column-wise order here. And then for the second column, we also get 3, 4. And that provides us this vector that has the results from the matrix. And if we want to do a replacement, replace all the elements of M1 that are greater than 2 with the value 20. So you already saw we get 3, 4, and 3, 4 from that expression. And now we replace, instead of just extract, with the value 20 in those elements. So let's play around some with this logical subsetting in RStudio. I'm going to start by declaring a matrix M that has elements 2, 4, 6, 8, 1, 3, 5, 7, 2 rows, 4 columns, and so it looks like this. Now let's try a simple operation with M. I'm going to look for even numbers using the modulo operator, which is the integer division remainder operation. If the result of that operation is 0, you have an even number. So let's try that with a logical subset of M. So I'm going to start with the matrix M and do my opening bracket. My operation is going to be M, and the modulo operator in R is the 2% signs. And then modulo 2, if this is equal to 0, we should have an even number. I close my bracket and I hit enter, and you can see that it extracts the even numbers out of our matrix. 2, 4, 6, 8. Remember, we're going in column-wise order with a matrix. We can go with the opposite. Find the odd numbers. M, left bracket, M, modulo 2 not equal to 0. And that extracts the odd numbers from this matrix. Let's try using the which function. W-H-I-C-H, and in parentheses, M modulo 2 not equal to 0. That gives us 5, 6, 7, 8. These are the indices of the odd elements in the matrix. So 5, remember, column-wise order. So 1, 2, 3, 4, 5 is our first odd number, which is 1, then 6 and 7 and 8. So which is giving us the index values of those odd numbers. Now let's do a logical expression that's going to combine a couple relational expressions. This is a single relational expression that we just did. So I'm going to say M, where M is even, equals 0, and M is less than 5. If you think about the results here, this part's going to find 2, 4, 6, 8, and M less than 5 is going to find 1, 2, 3, 4. This is going to get the logical AND result of this operation. So even numbers, and those numbers have to be less than 5, and you see we get 2 and 4 here. What happens if we use the logical OR? M, where M is even, or M is less than 5. So now it's going to find all the even numbers, is going to combine those with all the numbers that are less than 5. 1, 2, 3, 4. My guess at the result here is going to be the numbers 1, 2, 3, 4, 6, and 8. And that's what we get, although not in that order, because again we're going in column-wise order. But if you see 1, 2, 3, 4, and then here's 6 and 8. So you can see our expressions in their brackets for the logical subsetting can get fairly complex, and this can be a very useful feature. Now let's try which again. Let's just do which and find all the values M greater than 4. Now this is the index values. So this is not the values greater than 4, obviously, because 3 and 4 should not be in those results. But if we look at the indexes, this is 3, which is greater than 4. So index 3 is the value 6. Index 4 is the value 8. Both of those are greater than 4. We skip 5 and 6 index values, which are 1 and 3. And we get 5 and 7, which is index values 7 and 8. So these are the index values. But this should tell you we could do something like this. We could say M in brackets and then use that which result, M greater than 4. And this is going to give us the index values inside the brackets, which means it should extract the elements corresponding to those indexes. And you can see it does. So element 3 is 6, and that's the value we get 6. And then we get 8. And then we get 5 and 7. They're not ordered, but these are all the values that are greater than 4. Let's try a sort just to get those in order. Which M greater than 4, close our bracket and close our paren, and now we get those results in a sorted order. So we're combining these operations. We're embedding the which inside a subset inside a sort operation here, and it gives us the sorted order of all the values that are greater than 4. We don't need the which. This is just demonstrating that we can go in the reverse order here in terms of the evaluation of the expression. I could just say sort M. Well, let's just do M where M is greater than 4. And then let's just sort that expression, and that gives us the same result. So it's quicker, but this is just demonstrating that the which can be reversed, and then we can evaluate the results of it as part of an element extraction. Now let's look at some of the details of character strings in R. Character strings represent textual data, which can be letters, numbers, punctuation. In R, we use them a lot to represent categorical variables as opposed to quantitative variables. In other words, not numbers, but more descriptive variables. They're formatted as what we call extended regular expressions. Most of the time we'll just see them as regular strings, but they can take the form of something that represents something much more complex. Regular expressions are almost a programming language in and of themselves that allow us to manipulate strings, look for patterns, recreate patterns more efficiently, but they can be very complex. If you Google regular expressions, there's a lot of tutorials online, and I'd recommend taking a look at some of them, but we don't want to go too far into them because that is out of the scope of this course. We call our collections of characters strings, and that includes even if it's just a single character, and it can be no characters. There's a concept of an empty string. In R, we can use either double or single quotes. You need to be consistent with them. Either use all single quotes or all double quotes. Double is the preferred representation. Regardless of whether you use double or single quotes, they'll always be displayed with double quotes. So here I'm creating a string S1, hello from base R, double quotes, and it displays in double quotes. Here I'm creating the same string with a different variable with single quotes, but you can see when I display the contents, it shows as double quotes. Any value can be represented as a character string, so we can represent numbers as character strings, but this is a different data type, so we can't perform any sort of numeric operations on it. I can't create two strings, one containing 100 and one containing 200, and then try to add them together because they are not numeric operators. But if we try to do numeric operations, they won't work with strings. We can use relational operators to compare strings. The double equals for equality, the bang equals for not equality. So here I'm creating two strings. One has the word hello, and another one has the word hello, but with an uppercase H. So R sees these as not equal because of that case difference. Using the equality operator, we see that that's false. If we use the inequality operator, we see that that's true. When we compare strings, we have to consider the collating order. The way R does it is different from a lot of other programming languages. It's locale dependent in R. Locale is typically a geographic region, and there are different ways of comparing strings. So it could also be a language or a dialect of a language, and there might be different ways of comparing strings there as well. Most programming languages just use ASCII or Unicode encoding and the values represented by that encoding to compare. For instance, lowercase letters are considered greater than uppercase letters with ASCII or Unicode based on their numeric values. But for R, we use this collating order. Another name is lexicographic, and we can use the standard relational operators with these to compare them. Less than or equal, greater than or equal. There is a website that discusses the comparisons between different strings here and that locale specific comparison that's done. We normally are using English US, or US English here. This is the locale abbreviation that we use for that. Comparing it to a language like C, which uses ASCII, you'll see some differences in the results of these operations. So what we see here for this comparison is that the word hello with a lowercase letter is less than the word hello with an uppercase letter. So this is true when we do this comparison, and in other languages this would be false because the ASCII or Unicode value of lowercase h is greater than the ASCII or Unicode value of uppercase h. But for R, it's more of an intuitive comparison that we get lowercase hello is considered less than uppercase hello based on this collating order. Now here if we have two strings that are different, this is hello with an A as a second letter versus E, even though the uppercase H would be considered greater than the lowercase h, the sorting order, the ordering of the letters takes precedence, and so A comes before E, and so hello with an uppercase H is not greater than hello with a lowercase h because of that second letter difference here. So this just means you have to pay attention to how these comparisons are behaving in R if you're used to using other languages with different expectations on their results. I mentioned we can concatenate strings in R. For R concatenation, we use a function for this, actually two functions. One's called cat, which is short for concatenate, and one is called paste, which is more of kind of an intuitive name for the concatenation operation. There's a difference between these in that cat prints the results on the console but does not return anything. So if you want to display it without getting the result, you can just use cat. But if you want the concatenated result, then you need to use the paste function. Now both of these insert a space between the concatenated strings. So a couple of examples here. S1 has the value 100, S2 has the value hello from base R. So if we use the cap function and concatenate S1 and S2, and we assign it to a variable V, our display result shows 100 space and then hello for base R. So the concatenation operation is displayed here, but if I try to show the result as the variable V, you can see it's null. This assignment did not happen because cat doesn't return anything. Compare that to the paste function, assign the result of pasting S1 and S2 to V, and it doesn't display it, but V now contains the concatenated string. So these are the two functions you'll use for concatenation and the difference between them. One displays and doesn't return anything, one does not display but returns the concatenated result. As with other programming languages, we have escape sequences. This is the backslash with certain characters to give them specific behavior. As an example, the new line, \n, inserts a carriage return line feed sequence, which is a new line. In other words, it moves the cursor down one row and all the way to the left when it displays that escape sequence. So we've got two strings here, hello with a comma and world. We're running cat. Remember that just displays a concatenated result with a space between them. Now I'm using the new line as part of the hello string. So the new line, the \n escape sequence, is inside the double quotes, which delimit that string. And then the word world, and you can see that we get the hello comma, and then the new line causes the cursor to jump down to the next line and start on the left and print out the word world with that embedded space before it that cat inserts. If we don't want that extra space, well, I could just combine the strings hello and world and put the escape sequence in without the comma to separate them, and then we get hello and the world is left aligned with the hello on the previous line. Here are some other escape sequences. We have the escape single quote. If you want to put a single quote literal inside a single quoted string constant. So we have the single quote escape sequence, the double quote escape sequence, and this is for intermixing single and double quotes in strings that are bounded by the opposite symbol. We have a carriage return escape sequence. This will embed a carriage return, which is similar to a new line, but it doesn't include the line feed. In other words, it just moves down a row. We have a tab character. You can embed this and it will display as 4 or 8 spaces depending on the settings in your current environment. We have a backspace, the B following the escape character. This will backspace. The support of these really depends on your environment, depends on your console, whether you're in RStudio or just running from the command line. Sometimes they'll work, sometimes they won't. You'll just have to test them to determine which ones work in your environment and which ones don't. In this example here, we're assigning this string with a lot of bizarre characters in it to the variable s. So you can see we've got a escaped double quote, so it's going to embed the double quote in the string. And then the word tab, this is not the escape sequence for tab. Here's the escape sequence. So after the word tab and this space is going to embed a tab character in the output, followed by a space. Then the words B, S, and Y, 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 and then a backspace, and then an embedded quote. And so you can see there were 3 Y's here, but the backspace escape character works as intended, and it backspaces over the 3rd Y, so you end up with 2 Y's in this, and then the embedded quote. So you can play around with different patterns with these. It's interesting and it's good for formatting output, but don't depend on all of these escape characters to be functional in your particular environment. You have to test them out first. Using the substring function, substr, we can extract substrings. So given this expression hello world assigned to this variable foo, we're going to extract a substring from that variable that starts at index 7 and stops at index 12. So if we're counting from 1, H is 1, 2, 3, 4, 5, 6, and then 7 is this space character here, followed by 8, 9, 10, 11, and 12 for the D. So you can see some programming languages are exclusive of this last index, but R includes the character at that index when you specify the start and stop values. So we end up with space and then the word world assigned to this variable bar. Here I've got two variables, one containing the string Santa Claus, one containing the string Easter Bunny. I'm taking the substring of Santa Claus, starting at index 1, stopping at 5, so 1, 2, 3, 4, 5, the word Santa, and then I'm taking the substring from the Easter Bunny string, starting at 8, which is the word bunny, if you count the letters here, 1, 2, 3, 4, 5, 6, 7, 8 starts on the B, 9, 10, 11, 12 stops on the Y. So we're extracting the word Santa from the first string and bunny from the second string, and then we're embedding those substrings in a paste function as arguments to it, and it concatenates it into the string Santa Bunny. I mentioned using regular expressions, or that strings are formatted as regular expressions in R, although we don't always take advantage of the features provided by regular expressions. If we use the grep function, though, this is a Unix command that has been implemented in R. It allows us to specify patterns and then look for matches in a target of strings, or a vector of strings. So you can see for this grep function, the first thing we pass is a pattern. The pattern here, and this is, again, I mentioned it's like a programming language. If you Google regular expressions and find a table of all the possible code for these letters and symbols that we use, you'll see what they're doing with them. But this is specifying find one or more occurrences of the letter A. So we start with the letter A, plus sign says find one or more, at least one, and any other number of occurrences of the letter A immediately after the first letter. So in this vector of strings, you can see we've got ABC, so it finds the A here, one or more. DEF has no matches. CBA space A contains two A's separated by spaces, so it's actually going to match this A, but the fact that the next one is not immediately next to it internally is not really matching this A, but it only needs to find one, so it's happy with that. And then it finds AA, and it matches for that. Now we have a few arguments. Perl is a scripting language, and this is just specifying that the code used in the Perl language are also accepted in this particular call to grep. You can have true or false for that. So you have the Perl argument, and then you have this value argument. This specifies whether you want the grep function to return the index values of the matches it finds or the actual values that it finds. So here we see we matched in index 1, 3, 4 of this vector. Here's 1, here's 3, here's 4. But if we specify true for the value, then it returns the actual matched values. So it returns the strings, the entire strings, not just the matching portion. So we get ABC, CBAA, and then AA. So now let's talk about factors. Factors are variables, but unlike quantitative data, factors represent categorical or descriptive data. So it's a different type of data. It's not numeric, which has a continuous range. It's got a limited number of values. For instance, true or false, or gender of male or female. So here we have a vector of factors with the names Liz, Jolene, Susan. And so these are actually, they're strings, but they are treated as factor categorical data. There's 1, 2, 3, 4, 5, 6, 7, 8 possible values. We have gender, which is, in this case, just female or male. So you have 2 possible values for those. Then you have a birth month, which is the 12 months of the year. Well, maybe not in this case. We have 1, 2, 3, 4, 5, 6. July is repeated, and then 7 unique values. So we don't get all 12 because R doesn't really know about those. We're specifying that the only months we're interested in here in terms of this categorical data are these 7 months. If we look at the type of these factors, we'd see that they're character, they're strings. This is not a limitation, but it's just the way R treats them. But we can actually change their type and look at them as legitimate factor types. So here we're creating the factors. We need the vectors, and we did that already with our vector of characters, or gender, for instance, looking at it as character. If we want to force the vector to take on the factor data type, we have a function called factor that will do the conversion. And so this changes how R treats these values internally. Instead of just character strings, they become a factor, and we can do different types of operations with those. So I'm assigning the result of the factor function called on the gender vector to this gender.f, which is short for gender.factor variable. And when I display the output, you'll see here are the values. If I look at the previous slide, if I displayed gender here, I would see them as characters. But now if I do the type of with that variable, you see that they are not character anymore, they're integer. What it's doing is it's taking these values and assigning an underlying numeric value to them, integer, not continuous floating point, but a discrete integer value. And it'll give one of them 0 and one of them 1 because there's two possible values. When we're working with factors, the values they can take are called levels. Here we have our gender.f variable created from the gender vector, contains a character string. We display those values. The levels of factors are the two possible values. Here are the actual values of that factor, but here are the possible values. You have the two, female and male. So if we use the levels function and pass that gender vector, it'll describe the possible unique values, not all the values that have been assigned, but just the ones that it might assign based on the allowable values. We can change how we refer to those levels. We can use the assignment of a vector to the levels function result here. So this is assigning gender.f. This is just a named argument for the levels function, showing what we're passing into. But by doing this assignment with this vector, we actually change the names of those two factors from the full words female and male to just the initials f and m. So now if I display the value of that vector of factors, you'll see that it's using the short version based on our relabeling that we did here, and the possible levels are just f and m instead of female and male. So we can use factors to do subsetting with our vector. Here's a short list of first names with character values. This is the list from our previous example. And we had the assignment of gender, if we go back to that slide. So here we assigned in the order of the names, the gender, in a separate vector called gender. But remember, we converted that to factors. And so now we're taking this first name vector of character strings, and we are extracting the male data from the first names by giving the relational expression of gender.f equals male. And so this subsets and provides all the names that have male assigned to them. We do the same thing with the inequality operator. Gender not equal to male, and it finds all the names that have female or not male assigned to them. We can order the factors to do comparisons. Normally character strings, which the factors are by default until we change their data type, are considered as alphabetical. And so they have the normal alphabetical ordering. But we might want to provide a different context in how we interpret them. So here we're giving the weekdays of Monday through Friday. And you can see we're comparing weekday sub 3 to weekday sub 4. Is it less than? Is Wednesday less than Thursday? In terms of alphabetical order, it's not. So we get false for this. But what if we want to impart an ordering to the weekdays here in their natural occurring order, where Monday is first, Tuesday is second, Wednesday is third, Thursday fourth, and Friday fifth. So here we're using the factor function again, and we're providing the weekdays to provide the values as the x named argument. The levels are determined by passing that same vector in and letting it extract the possible level values. And then we provide this ordered equals true. And this says take the existing order that those values occur in. And you can see that we have the 5 unique values. So the data is Monday, Tuesday, Wednesday, Thursday, Friday. The levels are also going to be Monday, Tuesday, Wednesday, Thursday, and Friday. We're saying apply the ordering based on the sequence they occur. Now that we've done that, the ordering that they occur in is going to be used for our comparisons. And now if we compare weekdays.f, which is this new vector resulting from calling the factor function here, weekdays.f third index, which is Wednesday, is now less than the fourth index, which is Thursday. So now it ignores the alphabetical ordering and uses the sequencing that we provided by using this factor function here. In this example, we're using the factor function to provide all the possible levels. We're not going to use just the data that we already have Monday through Friday, but we're saying there are these other 2 days as well that we want to consider as possible level values. So we're passing Monday through Friday in our weekdays vector, but we're saying you could also have Sunday and Saturday. Now if we display weekdays.f resulting from this factor function call, you'll see that it's showing the data Monday, Tuesday, Wednesday, Thursday, Friday, and it's showing here are the possible level values. And it's going to show all these days. I've used an ellipsis to shorten this out for the display. Now another way we might want to create categorical data is to actually categorize numeric data. If we have a range of values, we can organize them into specific intervals and then categorize those intervals. We do this using the cut function. The cut function will break the range into the intervals as we specify them, and then it'll do the categorization for us into those intervals. We use cut with a range of values, and here we have 4 values, 0.5, 1.5, 2.5, and 3.5. We want to specify 2 intervals. Now for our intervals, we provide a vector of 3 values. The values used in this vector are taken as groups. We take the first 2 to create one interval between 0 and 2, and then the second interval goes from 2 to 4. This is showing you the categorization, the groups that R is putting these values in. These parentheses and brackets have special meanings. We see that we have the 2 intervals here of 0 and 2, and then 2 and 4, provided by these 3 break values. These are the actual groupings that R has done for those 4 numeric values in the data. So for the parentheses and brackets, the square bracket denotes inclusion in the range. The parentheses denotes exclusions. The number that has a parentheses adjacent to it is excluded from that range, whereas if it has a square bracket, is included in the range. So for example, in this interval, the parentheses indicates that 0 is not included in that range, but anything above 0 is, and anything up to the value of 2, or 2.0, because of the square bracket, will be included. So 2 is included, but 0 is excluded from it. In this example, both 0 and 2 are excluded from the range. So it would be any number between 0 and 2, but not including those values. Here we have 0 is included and 2 is excluded based on the parentheses. And here we have the inclusive range of 0 and 2, both included, as well as anything in between those values. So let's look at how we would do this in a more complex example. When we do this categorization, it's called binning, B-I-N-N-I-N-G, or the past tense here is binned. We're binning these values into discrete categories using the cut function. So here's a more interesting range of values, and this is not sorted. Notice we have 0.53, 5.4, 1.5, so on, up to 1.01. I'm specifying the intervals using this by vector, but I'm including 4 values. This means we're going to get 3 intervals out of this. An interval that includes or excludes, depending on how we define it, of 0 and 2, and then an interval with 2 and 4, and then an interval with 4 and 6. So we call the cut function with the data in the vector y. We pass our by vector as the breaks named argument. And here's how it categorizes them by default. Remember, the parentheses is exclusion. So for the first interval, 0 to 2, 0 is not included, 2 is included. So anything that falls in that range that is not equal to 0 will be in this first grouping. So the first number, 0.53, is included in this first grouping of 0 and 2. Here is the level value for that corresponding interval. Here are the other 2 intervals, 2 and 4. 2 is excluded, 4 is included, and then 4 and 6. 4 is excluded, and 6 is included. So this first value, 0.53, goes into this first interval. 5.4 is in the third interval, the 4 to 6. 1.5 is here. 3.33 is here, and so on. So you can see that it's grouping these into one of those three possible bins or levels based on the intervals we provided in our cut. If we want to switch the interpretation, we have a right argument, and we can specify right equals false instead of the default of true to reverse the brackets and parentheses. So here we're specifying that false value with our cut, and you can see now, if you look at the previous slide, 0 was excluded and 2 was included. Well, now in this example, 0 is included and 2 is excluded. So this determines how the brackets and parentheses are interpreted in those intervals. And this also means that some of the categorizations are going to change. So 2 on the previous slide was in the 0 to 2 range because it was inclusive of 2, but now it can't be included in that range. So it goes into the next range of 2 to 4 because the square bracket is inclusive of the value 2. So this modifies our categorization a little bit. And then we can take those ranges, the categorization in ranges, and give them names. We provide a vector with the range names, group 1, group 2, group 3. We had 3 intervals, same data as before. And now when we call our cut function, and this is just using the named argument for the data, which is x. We're using the same by vector as before. We're specifying false for right, and we're giving a labels argument of that groups vector we provided with the names. So now instead of the numeric range categorizations, we see a name categorization for each group. So the first value, 0.53, is in group 1, 5.4 is in group 3, 1.5 is in group 1, and so on. And our possible levels are group 1, group 2, group 3. So this is going to be a much more readable result versus having to process those numeric ranges when we look at them. So now we're going to hit the top level of complexity in our data types. We're going to talk about lists and data frames in R. Let's start with lists. Lists are basically a vector of vectors. You can store any type of data in a list. In other words, you can mix the types, whereas with matrices, vectors, arrays, we have all the same type of data. But a list, you can mix them. We use the list function to create a list. In this example, we've got vectors v1, v2, m1. We're not really concerned about the types they contain. Now, if we run this and get this li variable as a result of the function, we have 4 elements. Even though these vectors might contain multiple elements themselves, the list at this level does not dig down into that aspect of the data. It just looks at the number of elements as a whole that were added to the list. We can name these elements because a lot of times we'll want to extract them. We'll use the $ notation here to extract the elements from the list. Here we are creating a list with values of 1001 and applying the name number to that value. We're adding a logical value true to this list and applying the name logical to that value. And then we have a matrix, assuming we've predefined that, and we're saying give that the name matrix. When we display the value of the list, you can see that it shows us the names of those elements along with the associated values. Here's number, here's logical, and here's matrix. If we want to extract a specific element from that list, we can combine the name of the variable with the $ and the name of the element, and it will extract that element. So here we're getting the logical value, and here we're getting the matrix value by using the names that were given to those elements when we created the list. If we want to rename the elements, we can. We just assign a vector of corresponding name values to the list passed to the names function. So li is our list variable. We include it as an argument to the names function, and we use the assignment operator. In this case, we have the 3 elements. We're going to apply the 3 new names shown here to those elements. So now our list contains elements named my number, my logical, and my matrix. The data doesn't change, but the names of each element change. Now we can extract list elements using square brackets. There's a subtle difference though between whether you use double brackets or single brackets. If you want to get the actual element from the list you use double brackets. So here you see we're extracting the first element of our list, which is the value 1001. If we use the single brackets, you can see it's giving us the name of that element and the element value. If we look at the type of data being returned by each of these using the class function, we pass the single brackets, and you can see we're getting a list that contains that element, and that's why we see the name of that element included in the result. If we use double brackets, same element, you can see all we're getting back is the vector, which is a vector of element 1, but it's still a vector. And so this is the difference between using the double brackets and the single brackets when we do extraction with lists. We can nest our lists. We can have a list that's a member of a list. This does get complicated. You have to keep in mind the structure of your list. In this example, we're creating list 2 with the list function. We're passing a vector of these names of points, x, y, and z, and then we're passing these values for the x, y, and z points. And so we have list 2, and here are the elements of that list. Now we're taking that list and we're inserting it in our original list li using the $ notation. So we're creating a new element in our original list that consists of this list. And now if we manipulate that over here, here's the original list with a new element added. Here's my number, here's my logical, here's my matrix, and here's the element we just added, which is a list. And so you see it splits out that list into its constituent elements as well when it's displaying it. And it uses this two-level $ notation. $P is the name of the element in the top level list, and then each sub-element that's in that list is $point and $point value. So it's $P, $point, and $P, $point value. We can extract the elements from that nested list using the $. Here's the full list that's an element of our original list, and you can see it's basically the same list that we created. If we want to get at the individual elements of that sublist, we can use the $. So li is our variable, $P is the element we want to extract, and then we want to dig down one level further and get the point vector from that list, or get the point val vector from that list. We can also use square bracket notation. With double brackets, the fourth element is the list containing the elements point and point val. If we want to dig down one level further and get to the individual elements of that sublist, here's the first element, which is the vector point, and here's the second element, which is the vector point val. So you can see this might be useful for complex structures of data, but we do need to be careful that we don't take it too far because it could be very confusing to keep track of. Last thing to talk about in this module is data frames. Data frames are one of the most commonly used, apart from vectors, they're one of the most commonly used data structures in R. They are basically two-dimensional lists of vectors. Now remember, vectors contain all homogeneous element types. They all have the same element type. But when we combine multiple vectors in a data structure, that means we can mix data types within each constituent vector in that data frame. We group our data frames as a two-dimensional table. Each vector is a column, and each vector needs to be of the same length unless you want to do recycling. Each column, which is a vector, can contain a different type of data, but because each column is a vector, within a column, the data type is the same. To create a data frame, we use the data.frame function. So here we're creating some vectors to create our data frame with. We've got COP1000 section numbers. This is a vector of 4 numbers. Faculty is a vector of 4 names. Students, the number of students in a section is 4 numeric values. And then mean age is the average age of the students in each section. Now we're going to take those 4 vectors and combine them into a data frame. We call the data frame function, and we just pass each vector as an argument to that data frame. That creates, in the order that we provide those vectors, these 4 columns: sections, faculty, students, and mean age, organized as a table of rows and columns. You notice it provides row numbers in front of each row when it displays them. If you want to extract data from a data frame, we can use square bracket notation. The second element of the data frame is a column. It's the faculty column. So here's element 1, here's element 2, here's element 3, here's element 4. So at this level, a single index, you're going to get a column of data when you extract it from the data frame. Now, any data in a data frame that's string is interpreted as a factor. This is just the default behavior of R. Remember, factors are categorical variables, and the levels are the possible values the factors can take based on the data that's provided. So if I am going to show the value of the faculty vector, second column, and I want to drill down to the second row to get a single element from that data frame, and notice we're using the 2 index comma separated extraction notation here. So I'm going to the second column, second row, which is Jones, and it prints the value of Jones, and it's also going to show the levels, the possible levels: Ellison, Harrison, Jones, and Smith, which corresponds to the data we provided for that column. So it's interpreting those names as factors. Now, just as an aside, if we don't want this print function to display the levels, we can provide this named argument max levels equals 0, and it won't display those when it displays the value of the extracted element. But more importantly, if we want to avoid categorizing those strings as factors, and a lot of times we don't want them to be interpreted as factors, we just want them to be interpreted as character strings. So to prevent this, this is a very common argument we're going to provide to the data frame function: strings as factors. It's a logical value. It's going to be true or false. By default, it is true. That's why, by default, R treats strings as factors when it creates a data frame. So let's add that argument to our data frame command. Strings as factors equals false. And now if I run the structure function str is a very common function we run to look at the internal structure of an R object, similar to the class function we ran a couple slides ago. Although that just shows the type, this shows more information about our object. So our data frame is called COP1000. We're passing it to the structure function. You see it's indicating we have a data frame, 4 observations, which is basically 4 rows of data. Observation is a row of data of 4 variables. That corresponds to the columns. So we have COP1000 sections. That's our vector with the numeric values here, and you see it's interpreting those as numbers. And you see here for faculty, it's now interpreting the names as character strings instead of factors. So now it's just plain old character data. And again, a lot of times this is what we want when we create a data frame, by using that strings as factors argument. And then we have the other 2 numeric vectors that still take the same form as they did previously. So strings as factors is a very important argument we pass when we create a data frame to make sure it's not interpreted as factors by setting it to false. As with lists and arrays, we can name the column names, the element names in our data. So here we are again using the names function, passing the data frame we just created, and we're assigning the 4 element vector here of these strings to the result of that names function, which is going to rename our columns. If we go back a slide, we can see we had COP1000 sections, COP1000 faculty, students, mean age. And if you notice these, when we create the data frame, it's using the name of the vector as the column heading. So if we want to simplify that, we're using this names function and reassigning those names, and now it's given us a more meaningful name for each of those, whereas we have sections, faculty, num students, and mean age. So we have a more concise naming scheme for those columns now. Same data, it doesn't impact the data, but it changes the column headings for us. And again, this is a very common thing we'll do, because when R imports data, a lot of times the column names are very awkward and very cryptic in some cases, and might even contain special characters. And so we want to give them more normal names. If you remember, we added columns to a matrix using cbind. We can add a column to a data frame using cbind. In this case, we have our COP1000 data frame, we want to add the average score for the course as a column to the data frame. So we're going to create the vector, average total. Here are the values, 4 values. We need to match it up with the number of values that are already in there. And we're using cbind to add to the data frame COP1000 the new vector. And so you see the result here. It adds onto the end of that data frame the new column with those values. We can also kind of take a shortcut, and instead of using cbind, we can just use the $sign notation. So we have this vector, and we're going to create a new column that's called average total. COP1000 $sign average total, assign it the average total vector, and it adds the column. So this is an alternative to adding columns to your data using this $sign notation instead of cbind. To remove a column from a data frame, you set the column to null using the $sign notation. So that average total column we just added, let's get rid of it. COP1000 $sign average total, assign it the value null, and you see now it basically just deletes the column from the data frame. If you want to add rows to a data frame, well, rbind. A little more complex than cbind. You have to have names that match the original names for the new data. Here we're going to start with a temporary data frame called new data. Using the data frame function, we're passing new values. You can see these correspond to the COP1000 data frame we created originally. We have the section number, we have the faculty name, number of students, mean age, and then the average total score. So this is assuming we have added that average total column back in. And so here's the data frame. And look at the names it gives the columns. 2794, it calls it X2794. Brown is called X.Brown, X31. These are not meaningful names. These aren't really useful for us. So before we do the rbind to add this row to the data frame, let's set the names, and they need to be the same names as in the existing data frame. So we're adding the names, sections, faculty, num students, and these are the new names we gave the data frame back in slide 54 here. And so now we've given the temporary data frame the same column names as the original data frame, and we're going to add this row to the original data frame using rbind. From that point, it's simple. It's just calling the rbind function, passing the data frame, and passing the new row, and it appends it to the end of the data frame as shown here. So now we have 5 observations of 5 variables. Now, one thing we can do with our data frames, as we did with our arrays and our matrices, is we can do logical subsetting. As an example, let's find all the course sections that have more than 20 students. The notation we can use here, using the $sign notation with a COP1000 data frame, we can use the $sign notation and specify the column name where we want to apply this expression. Num students has an embedded space here, so because of that embedded space, we have to include quotation marks around the column heading. If it did not have an embedded space, we wouldn't have to have the quotation marks, but in this example we do, and that's okay. We'll just apply them around the column name. So the expression we want to test is COP1000 $sign num students greater than 20. Based on the data, we get the result true, true, false, true, true. If you go back to the previous slide, you see for number of students, here's true and true. The third element is false, the third row, there's only 19, and then true and true. So we should have true, true, false, true, true, and that's what we have in the results here. So our expression is good. Now we need to plug it into square brackets to do the logical subsetting. So it's COP1000, and then COP1000 with the quoted column name of num students greater than 20. That's our logical expression. Now it's very important because we want to extract the entire row. For each row where this expression is true, we need to include this comma inside the square bracket. This says, give me all the matching rows and then all the columns. And then we close it off with the other square bracket. So it applies that expression, and you can see it extracts each row where the number of students matches that condition, and we get all the data associated with that, and we get the expected 4 rows out of that. Now the index here is consistent with the index of the original data. So it's not going to renumber our row numbers here, or our row index values here. It's just going to give us the 4 results with the corresponding row number from the original data. And so this is a real useful feature we can do. It's a very powerful feature we can do to extract data that matches a specific condition from our data frames. So let's work through a sample exercise using some of the concepts we've covered in this module. We're going to create a data frame with the data that's included in this table at the bottom of this slide relating to local farmers, their harvest quantities, their harvest dates, and their crop categories. All of the data that we need is in this table, but we're going to incrementally add some things. We'll start with a basic data frame, which just consists of the farmer, the harvest amount, which is, I'm referring to tonnage here, harvest date, and category columns. We have simple farmer names here. The tonnage category is numeric, as you can tell here. Harvest date, just various dates in the spring when they harvest. Category was interesting. If you do a little research, you can find some websites that cover agricultural categories. And so I've pulled a few of these. I actually made up the greens category, but grains is definitely a category. Ornamental, this is for gardening. So there are farmers that are devoted to doing farming for gardening purposes, ornamental plants. Industrial was interesting. This includes rubber and tobacco. There's also oil farming for crops like corn and canola. So I've included a few of these, and we're going to specify more than what's shown in the category here as we create this data frame. I'll give you that data as we go through it. These other columns, priority, hiring, we'll create those dynamically after we've done the basic data frame. So we're going to want to refer back to this table to get our data, and there's going to be a lot of manual data entry here. Bear in mind that typically in R, we're going to bring in data from a file of some sort, for instance, a comma-separated values file, or maybe from a website. But in this case, we're just going to be entering this data in manually. So I'm going to go to RStudio, and I'll flip back and forth between this slide. First thing I need is a data frame with farmer, tonnage, harvest date, and category columns. I'm going to start with my data frame. I'm going to call this farm.data, and I'm going to use the data frame function. Now I'm going to do multiple lines of input here. As in the slides, I used separate vectors. I created the data vectors first, and then I appended them, or I created the data frame using those vector variables. I'm going to manually enter the data vectors here as arguments to this data frame command, though, for this example, just to show you a different way to do this. So if I just hit enter here, I get my plus sign, which says R is expecting more input here. And I'm going to start with my farmers category and use the equal sign, not the arrow assignment that we do for an R object, but this is for a column. I actually use the equal sign here. And I'm going to do a vector with the names of the farmers, which are Brown, Jones, McDonald. Make sure you put your quotes in there for strings. And Byers for the first 4. We're going to add Smith as a row, as an R-bind operation later. So these are my farmers, their names. The tonnage data, return, there's my continuation character. Tonnage equals a vector, and the numeric values, 2.5, 3.7, 1.9, 7.1. Close off that vector, comma, my harvest date, vector, these are character strings, so May 20th, April 30th, May 15th, and June 1st. So there's my harvest dates. Now for the category, I want to use a factor, not just a character string. It's a categorical variable. And so my column name is category. And we're going to use the factor function. Now this is inside my data frame function. So we can use an embedded function here to create our factors. I'm going to do a vector of greens, grains, greens again, this is based on the table in the slide, and ornamental. Now this is the first argument to my factor function, this embedded function that I'm calling here, the vector containing the factor values. Remember that this can be a subset of all possible levels for this factor. When we saw the weekday example, we used Monday through Friday, but Monday through Friday and Saturday and Sunday were possible level values. So I'm going to add those values in addition to the ones I provided using the named levels argument inside the factor function. And this is going to be a vector. So now I'm going to enter the level values here. Greens, grains, fiber is another category. Ornamental we're using. And a couple other categories I'm going to add here are feed and then there's industrial. So these again are just agricultural categories that I have obtained from the web just doing some simple research on the possible values. So I'm closing off this levels vector here. So I need an extra right paren to close off the factor function. So this is the entire category column I'm creating here with those 3 lines. Got a comma, and then remember this is an important argument. Strings as factors equals false. I don't want to interpret any of these string values as factors unless I specify it by using the factor function here. I close off my parenthesis and I hit enter, and now my data frame is created. I can type it to see it, and you see the farmers, the tonnage, the harvest date, and then the categories that we're using based on this factor function call. It doesn't show all of them, but they are all included as possible levels for that factor. I can verify that by doing a structure command, str farm.data, and here's my data frame. There's 4 rows or 4 observations of 4 variables, 1, 2, 3, 4 columns, and each of the columns, and you can see the category is a factor with 6 levels. Here's 1, 2, 3, 4, 5, 6, but I'm just using 4, greens, grains, greens, and ornamental. Notice what R does with this column. It's converting these levels to numeric values in the order they occur. Greens is assigned 1, grains is assigned 2, fiber 3, ornamental 4, 5 and 6 for feed and industrial. So here you're seeing the numeric value of those factor levels as assigned for that column. Greens is 1, grains is 2, greens again is 1, and then ornamental is 4. So you see the numeric values of those levels assigned to this category column when you look at the structure of the data frame. Our harvest date is character, as expected. Those are dates. Our farmer names are character, as expected. Those are character. And our tonnage is numeric. Now, sometimes when you read in numeric values from files, it will convert them to character strings, and you might need to convert those values to actual numbers. If I had to do that, I would do something like farm.data and provide the column tonnage assignment, and there's a function called as.numeric. As.anything will convert one form of data to another. So if this were character string data, running as numeric, farm.data tonnage, $tonnage, this would convert that column from character string into numeric. But you can see that when I created the data frame, it was already considered as numeric data, so we don't need to perform this step. So here's a basic data frame. Go back here and we've completed this step. Next step, we want to add a column indicating each farmer's hiring status as yes or no based on this data. Brown is yes, and remember we're only working with these first 4 rows for now. We're going to add the row for Smith in a minute, but we have yes, no, yes, yes for hiring for those farmers. So to create that column, I'm going to use a $sign notation. Farm.data hiring is the name of the column. Assign it Now these are yes/no values, so they're going to be factors with the values of y or n. We could say the full word yes or no. I'm going to use a shortened version of just the letter. Factor and the vector yes, no, yes, yes. So farm.data hiring, check what we just created. Okay, spell it right. And you can see the values, yes, no, yes, and yes. Look at the way it's ordering them. It's based on the alphabetical or the sequencing order. So no is coming first. Even though yes was the first value we specified, no is coming first, which means internally it'll have a numeric value of 1, and the level y will have an internal value of 2. By using this notation, I've added it to our data frame. If I just look at farm.data, you'll see it's added the column here. Do a structure again, just to take a look at the structure of the data internally. And here are those factor values. Remember, yes had a numeric value of 2 internally. No, yes, yes. These are the possible levels. So I've added the hiring status. Now I want to reorder the columns. To reorder the columns is really easy. You just specify the order that the columns occur in the data frame that you're desiring. So to do this, I'm going to say farm.data and use farm.data again with the square bracket notation. Now I'm not going to change the order of the rows, so I'm just going to put a comma there. The rows are going to stay as is. I'm going to change the order of the columns. I need a vector, and the vector contains the columns in the order I want them in. Column 1 doesn't change. The instructions say we order the columns to move the hiring status to column 2. So you see here the final version, hiring is column 2, but currently it's column 5. So I need to move it. So 5 is going to go in the position where 2 currently is, and then the rest of the columns stay in the same order, 2, 3, 4. Close off my vector. Close off my square bracket. Let's check it again. You see now the hiring column has been moved to column 2. So we're good with this to this point. Now we need to add the farmer Smith. Smith raises industrial crops, is hiring, produces 5.4 tons, April 15th harvest date. So let's use rbind to add that row. Now in the slides I used a new data frame, and I had to sync up the column names in order to do that. But if we just provide the data dynamically, we don't have to do that. So here's how I'm going to do the new row. Farm.data rbind and farm.data as a first argument. And then the row as a vector. C. Now I need to provide the columns in the order, the data in the order that the columns occur. Smith is the name, that's first. Hiring is yes. 5.4 is the tonnage. April 15th is the harvest date, and the category is industrial. If I type that in right, it will recognize that as a factor for those categories. Farm.data, and here's our new farmer. Check the data, everything works across. Do a structure just to take a look. Farm.data. Now it's 5 observations of 5 variables. And you see the new industrial column value that we added to that 5th row. So I've added the observation here. Now we want to create a vector of priorities. The idea here is that we've been asked to determine which farmers meet the criteria of green producers with an average harvest of more than 2 tons. We're going to give them a supplemental funding status priority of high priority if they meet that criteria, but low priority if they don't. So I'm going to create a factor variable, a factor vector of priorities. To do that, I am going to give it a name, prio vals, and it's just a vector, low and high. Now I want to create a column of data that's going to use logical subsetting to determine which farmer gets which priority value. So I'm going to do priority is my new column name, and I'm going to use this vector, prio vals. And this is going to use the vector-oriented behavior with a logical subsetting to select after applying a relational expression. Relational expression is farm data tonnage is greater than 2, and this is using the element-wise and, the long and, if you will, not the short and. I want to look at every element here. And farm data category is greens, based on the criteria that was provided here. Greens, average harvest of more than 2 tons. I'm going to add this to the column as a data frame. And you can see the results here. I should have a high priority for brown with 2.5 tons in greens. Nobody else matches that criteria, so they are all low priority. So by doing this, the expectation is I'm going to apply either low or high to this priority and assign those values to the vector. So if I do this, I'm going to check my results before I add this as a column to my data frame. You see, I only get one L, a single L. That's not what I expected. That's not my vector-oriented behavior where it goes through and it checks each element. Although it actually is. If we look at what's going on here, prio-vals is 2 strings, low and high. If we're treating this as a vector, we can use our indexing to specify prio-vals sub 1 is 1 and prio-vals 2 is high. So prio-vals 1 sub 1 is low, prio-vals sub 2 is high. Look at the results of this. Remember that true and false correlate to the numeric values 1 and 0. So if we look at the results of this expression, let's just take this relational expression. Look at the result. Okay, tonnage is true, true, false, true, true. It applies it to each farmer, each observation in the data frame. This one, category of greens, true, false, false. Now apply the logical and. True and true means the first column is going to be true based on both conditions being true. The rest of them are all alternating true and false. The rest of them are going to be false, and that matches with what we expect in our data. So why aren't we getting the expected results? Remember that, again, false is 0 and true is 1. So if this expression results in false, it's looking at prio-vals sub 0. What is prio-vals sub 0? There's nothing there. Remember, our indexing in R starts with an index of 1, not 0. So we want to get a 1 for low priority here for this element and a 2 for this element. So how do we fix this expression? I'm going to go to this extraction, this logical subset operation, and I'm going to add 1. So now if it's false, it's going to give me 0 plus 1, which is 1. That's low. If it's true, it's going to give me 1 plus 1 is 2, and that's going to give me high. So now if I run this priority, you see, using this little trick of the internal representation of our true and false values and a little bit of math, we come up with the expected values. High priority, low, 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 low. That's what matches up with our column here. From this point, all we need to do is add this as a column to our data frame. Farm.data priority, using the $sign notation, and assign it this priority vector. Print it out, and you can see it added the priority over here with the proper values, and then everything else should match what we have in this table. High and 4 lows, and that's what we've got in our resulting data here. So this just is an example of various things we can do to manipulate a data frame, add data to it, use a logical subsetting, and include that kind of dynamic data in our data frame as we create the data. One final note for this exercise that I just finished. I've been doing everything interactively in the workspace for RStudio. It would be easier if I created a new script file, new file, rscript. Now for our assignments, of course, you're going to need an ID header at the top. So you'd put assignment, whatever the assignment was, .r, and your name, date you create the file, description, creates data frame representing farm data. So for this type of assignment, you'd have an ID header like that, and then you'd enter your R commands here, minus the continuation character I've just copied and pasted. And this way you don't have to do all the retyping if you mess something up. It's much easier to edit the code, save as test.r, and then we can run this. And it's going to do everything that we've done interactively through this script. Much more repeatable, much more maintainable, much easier than just doing everything interactively. So this would be the preferred way to go about it.